All right, everyone. Hope you guys had a good weekend and parent-teacher conferences went well. And yeah, so we'll do a quick little video, and you have a homework assignment on force and Newton's laws. This should be a pretty straightforward. It's still what I'm going to ask you to do today is still mostly kinematics, so it should be pretty familiar. But we're going to take it one step further as we start getting into force. But let's start out with Newton's laws. We aren't going to be using all of them really too big today, but let's go through them here. So Newton's first law: an object in motion will remain in motion unless an outside force acts upon it. An object at rest will remain at rest unless an outside force acts upon it. So let's talk about what that means, right? Because as a law, it's like kind of, I mean, it's a lot of words there for a very simple concept. All right, so let's break it down. To end motion or to start motion, okay, what has to happen? Motion is like velocity, right? And if you want to stop or start that motion, you need acceleration. So, right? So what this law means is that forces, right? So if to end motion, we need an acceleration. An acceleration ends those motion, and a force will. And so unless there's a force, there won't be an acceleration. So basically, this is telling us forces cause accelerations. Okay. All right, that's all it's telling us. Second law, straightforward, just an equation. The net force is equal to mass times acceleration. Okay, since forces are kind of like pushes and pulls, like, right, to get the same acceleration, you have to push harder to get a more massive object to do it. And finally, this is the one that you've probably heard before most, but you've probably heard it the wrong way. For every action force, there's an equal and opposite reaction force. You've heard it without the force there. It's not true without the force there. So let me explain a little bit more about what this is. An action force. It's like the action force is you pushing, you pushing a wagon, a wheelbarrow. Okay? So that's the action force here. You pushing the wheelbarrow. Okay? Now, what's the reaction force? Is the wheelbarrow pushes you. Now, that doesn't make a whole lot of sense to me, right? If you push on a wheelbarrow, you don't really feel the wheelbarrow pushing back on you. It sort of is. I mean, like, like you have to kind of, if you think of like a really heavy wheelbarrow, you got to push, but it's definitely like you're not going very fast, even though you're pushing hard. But there's a better situation that's going to make it more clear. Okay, so what if you're on ice or on a slip and slide? So you're both standing on a slip and slide, right? So you push someone and you get pushed back, right? So if you're on something slick and you push someone, they go backwards, but then you also get pushed back. And the big thing is that those two forces are equal. So if I push someone, right, I also get pushed back. And it's most obvious on slip and slide. Here's even a better example, right? This is probably the best example. You're canoeing. You push off someone else's canoe, right? You push their canoe, right, and it pushes them back. But you also you push someone's canoe, and your canoe gets pushed back, right? Both of you end up moving. It's not just them. All right. So that's really it is. It's most obvious when there's no friction. If there's friction, it's a little bit harder to recognize what's happening, but it is happening. All right, so a little more details about force. A force, so because forces cause acceleration, a force is anything that could cause an acceleration. This could is important, all right, because you don't have to. Like right now, I am not accelerating. And gravity is still pulling on me. The force of gravity is still acting on me. I'm getting pulled down towards the earth, but I'm not going anywhere. So even though gravity is acting on me, right, I'm not accelerating. But in some circumstances, gravity could accelerate me. If I'm jumping up and down, gravity is accelerating me when I'm in the air. So we have to be careful. So just because it's not accelerating you right that second doesn't mean it's not a force. Okay, so you got gravity, magnetism. Those are the two ones that basically can do it without touching you. All the other ones like pushing, pulling, friction, those sorts of things, they have to be, the two objects have to be in contact. So you're looking for gravity, magnetism, and anything that's touching it could be exerting a force. All right. Because net force, right? Net force is what forces are what cause accelerations, right? If you push something one direction, it's going to accelerate in that direction, right? So net force is always the same direction as acceleration. Force is measured in newtons. That's the unit, and that assumes that mass is measured in kilograms. Okay, so just keep that in mind. These two, newtons is the unit of force, and if you're calculating force, you want to use kilograms for mass. All right, so we got a few examples and we're just using basically this equation right here, right now. F net equals ma. All right, so a 700 kilogram car's engine can produce a maximum force of 3,000 newtons. How long will it take to go from 0 to 60 miles per hour? So first off, let's convert. 60 times 1,600 over 3,600. Right, because this is seconds in an hour, and this is meters per mile. All right, so we do that, and we should get that it's 26.8 meters per second. Okay, so that's the first. We got our conversion. All right, so we got V final equals 26.8. We got V initial is 0, right? And those are the only two kinematics values we have. And I want to find time. So I got to get one more, and that's acceleration. I can get it because, right, F net equals ma. So if my force is 3,000, and that's equal to 700 times a is going to be equal to 4.29. Right? Now I have a third kinematics variable. I can use V final equals V initial plus AT. 26.8 equals 4.29 t. Time is going to equal 6.25 seconds. Okay? So, kinematics, and we're adding in this additional piece, the F net equals ma. Most of what we're doing. All right, same car. 700 kilogram car, and this is now counting the passengers, and it's still producing 300 newtons force. I want to know what is the net force on the 50 kilogram passenger. So, we've got a couple of things to note here. We know the acceleration of the car is still 4.29 meters per second squared, right? That's not going to change. It's the same mass and same force. Now, if you're in a car, the acceleration of the car has to equal the acceleration of the passenger. So some of that force is being transferred further from the car to the passenger, and we can actually figure that out, right? So F net on the passenger is equal to 50 times 4.29, and that is 215 newtons, right? So just know, like, the acceleration of two objects that are like intertwined, like you're inside the car, you gotta have the same acceleration as them. All right, a 100 kilogram astronaut throws a 3 kilogram tool in frustration during a spacewalk. If the 3 kilogram tool experiences an acceleration of 30 meters per second squared while in the astronaut's throwing motion, what acceleration does the astronaut experience? Okay, this is just like the canoe thing. If I throw something forward, I'm in outer space, I get pushed backwards. So, this is, right, the force on the astronaut is equal to, it's not how you spell astronaut, is it? You have it right up there. Is equal to, right, the negative force on the tool. Right, so we have, because we have a person, we've got the force on them, and we've got the tool, let's say it's a hammer. I'm sure they don't actually use hammers in outer space, or, you know, right? We got these two forces: force the astronaut, force the tool. So they're just opposite directions, right? So if the tool's acceleration, right, the force of the tool is equal to mass of the tool, right? This is 3 times 30. And the F-force of the astronaut is 100 times acceleration of the astronaut. This acceleration of the astronaut is negative 0.9 or meters per second squared. Right, it's just the opposite direction of the tool. Right, last one here. 600 kilogram Newton starts from rest and accelerated by 3,000 Newton force from the engine for 6 seconds. Then the driver hits the brakes and the car travels, hits the brakes, or it says, and comes to a stop. In total, the car travels at 135 meters. Okay. What is the force in the car when it is braking? Okay, so first off, forces cause accelerations. And I've got two different forces. I got the force from the engine and the force from the brakes. Engine for the first part, brakes for the second part. That tells me this is a segment problem. It's got two segments, right? It's got the accelerating part and the braking part. Right, during the acceleration part, we've got V initial equals 0. It starts from rest. We've got F net equals MA, which is 3,000 equals 600 times acceleration, which means acceleration is 5. Right, and I've got time is 6 seconds. So, in a two-part problem, what do I need to find? I need to find the final velocity. So V final equals V initial plus AT. And we should get that V final is 30 meters per second. So now this is the V initial here is 30 meters per second. Okay, the V final is 0. Okay, and I don't need to have another. I don't need another variable here. But I have this 135 meters. So what if I found the displacement here, right? So change in x equals V initial times time plus 1/2 AT squared. I get that this is 90 meters. So this part is 135 minus 90, or 45. Oh, shoot. Don't do that. There we go. All right. Need to erase that. All right, so now I've got three variables. V final, V initial, and displacement. I want to find force. So I'm going to find acceleration, right? So I got V final squared equals V initial squared plus 2a, change in x. 0 equals 900, right? That's 30 squared plus 2a times 45. So negative 900 equals 90a. A equals negative 10 meters per second squared, right? This is negative because it's going the opposite direction of velocity. That's good, which means my force is going to be 600 times negative 10, negative 6,000 newtons. Okay, and the negative, of course, is just direction because force is a vector. I should have been clear about that, but when we're talking about F net being in the same direction as acceleration, net force, it's got to be a vector, right? It's got to have direction. So it's the opposite direction there. Okay. All right, that is it. Again, try the WebAssign. It should be pretty straightforward. Problems are all like that. All right.